Hello, this is Richard B. Rood, and this is a module in my course on climate change and climate change problem solving. In this module, we will talk about feedbacks to warming, and we will focus specifically on the feedbacks associated with the physical climate system. In an earlier module, we talked about Earth's energy balance, and we talked about the idea that the Earth and climate was a discipline and a study that required one to think about systems. And that once we had a system, we thought of that system being in balance. And with that balance, then we would be able to alter that balance by changing something. And that change, in our case, is primarily carbon dioxide increases in the atmosphere. So the question now is, once we start that change, once we start to warm by adding carbon dioxide to the atmosphere, how does the climate, how does the Earth react or respond to that? Does it, after that initial warming, recover? Does it run away, or does it collapse, meaning go the other direction? So run away, I mean, does it get warmer and warmer, or does it collapse and get colder and colder? Or does it go to a new balance, or perhaps something we'll call a dynamic balance? For this, if you want more information, the Wikipedia article is actually quite good. Or in our online book, Andrew Gettleman and I discuss feedbacks in chapters 5, 7, and 8. So I want to revisit the idea that we're dealing with a system and that it's in balance. I want to extend that idea to the balance of many things. We often think of our economy or our markets being in balance. And if you listen to economic news, then you'll hear a lot about the Federal Reserve and that what is the job of the Federal Reserve? The Federal Reserve, primarily through managing of interest rates, tries to control inflation. It also balances that control of inflation with full employment. So there's this idea that there are competing attributes of our economy that can be balanced by something that might be a relatively small, almost like a thermostat, and in this case, that would be interest rates. Another thing that I like to think about is markets. How do we watch movies? If we look at over this period of time from 1950 to 2018, we'll see that we watch movies first in theaters, then we saw it on TV, we saw video cassettes, then we went to DVDs, and then we went to firms that were renting DVDs like Blockbuster and originally Netflix and now Redbox, and now we look at movies many times through online streaming. We still look at movies, but we had a market. And I can assure you that there was a time when I thought that movies on video cassettes were sort of the end of where we would be. But there was disruptive technology, the balance was changed, and we went to new media for looking at movies. So this idea of balance is something that, if you think about, we experience all the time. Here's another one. This is an ecological one, perhaps, or a famous dynamic balance, a dynamic equilibrium, perhaps, called the predator-prey paradigm. And in this case, we'll use a lynx, this cat here, and a hare, this rabbit here. This idea, here's the population of the hare, which goes up and down like this, grows when there's a low lynx population. As the lynx population increases, then the hare population comes down, and you see both of these are cycling somewhat out of phase here in this equilibrium of population of the lynx and the hare. And we have dynamic balances in the atmosphere or in the climate system as well. This is a figure that appeared in earlier modules of this series of carbon dioxide and temperature over the last 350,000 years in this case. And what it shows is that carbon dioxide and temperature here are closely related to each other. Their correlation would be very high if you were to actually calculate a statistical correlation coefficient. There are times of low temperatures that have glaciers. These are the ice ages, and the carbon dioxide is below 200 parts per million. And then there are times of high temperature associated with CO2 of less than 300 parts per million. So we have this dynamic equilibrium between the ice age and the temperate zones, and the carbon dioxide is doing this change of about 100 parts per million. Again, this is the idea perhaps of a dynamic equilibrium. Returning to another figure that we talked about earlier in this series, here is a picture of the radiation balance of the atmosphere taken from Keel and Trenberth in 1997. And the basic idea here is there's incoming energy from the sun, there's reflected solar radiation, there's outgoing long-wave radiation. What we talked about when we analyzed this figure was that the way that you can change or influence the energy balance of the Earth are through things that change absorption, things that change reflection. There might be changes in the sun, though we do not control those. And then there's energy can go down away from the surface of the Earth, perhaps into the ground, or more realistically, energy that is going to be going into the ocean, or perhaps accumulating in ice, and in that case, likely melting ice. And then what we are doing to change this balance is we're changing the carbon dioxide, which are one of the ways that you can change the absorption of energy. So I think it's important to think about in terms of trying to think about how do you analyze any particular situation in the energy balance, is that the primary mechanisms of changing the energy will be how do we change things that reflect or things that absorb. So we get to the idea of feedbacks. The intuitive idea of a feedback is how do you react to something? If somebody steps from behind a corner, what do? Do you stop your pace to not run into them? Do you flinch because you're fearful? Perhaps some people even attack, who knows? But there's some sort of reaction. If a tire goes flat while you're driving, what do? What is your reaction? Or if you start to slip on an icy sidewalk, do you respond in such a way to keep yourself from falling, or do you fall? Going back to above in the dynamic equilibrium, what is the response when too many lynx eat too many hares? Here's an acrobat who is balancing on a tight wire in a circus. She has her leg up in the air and she's holding it. She has an umbrella. And you can imagine that there are all sorts of things that are causing her potentially to lose her balance. There might be wind blowing in the Colosseum. There might be general jiggling of the wire, instability in the foundations that are holding the wire at the end, just her breathing, her heart rate, for example. And so if she's a successful and good acrobat, what she does is that when one of these perturbations or one of these changes happens, she responds in such a way to hold her center of gravity in a certain place and maintain her balance. So that's the idea of a feedback. There is some change to the system, and it may be quite a small change, and the system changes in some way in response to that. So the definition of a feedback is when the outputs of a system are fed back as inputs or forcing to the system. And so many engineers would see this in an electrical engineering course as the representation of an amplifier. And if there's a negative feedback, then it regulates the system. And if it's a positive feedback, then the system might explode or implode. Just for the benefit of those who have seen this, and the engineers and perhaps scientists, this is a circuit diagram of an amplifier. And then what's happening here is there's a signal that goes into the amplifier. There's a signal that comes out of the amplifier. Some of that signal goes back and adds to the signal going into the amplifier. And the question is whether or not this system is designed in such a way that keeps this from, say, squealing when this sort of feedback happens. The idea is we perturb the system, and how does it respond? In order to dissect or deconstruct perhaps some of the complexity of the climate system, it's worth remembering what our greenhouse gases are. And our primary greenhouse gases are water vapor, carbon dioxide, methane, nitrous oxide, ozone, and the chlorofluorocarbons. We add to these greenhouse gases particulate matters in the atmosphere called aerosols, which also will complicate the radiative balance. What we're going to be most interested in right now is to hold some of these attributes in mind. What we're doing is we're increasing the carbon dioxide in the atmosphere. There is a lot of carbon to release, and we like fire. So right now, if we were to do a budget calculation and look at the imbalance, what we find out is that the increase of carbon dioxide in the atmosphere can be primarily attributed to fossil fuel burning. There's a whole lot of water in the atmosphere, and it cycles between its different phases: ice, the solid, liquid, and gas or vapor. And water is a very strong greenhouse gas. It is, in fact, the most important and the dominant greenhouse gas. But because of this large amount of water in the reservoirs, it's something that we generally think of as responding to the carbon dioxide increase, as opposed to, say we're increasing water. There's a lot of methane on Earth. Nitrous oxide is related to agriculture and fertilizer, and these manufactured greenhouse gases, such as the chlorofluorocarbons, can be very potent. If we focus just on carbon dioxide and water vapor, they're both part of the biological cycle. Oceans can always fill up the atmosphere, that is, provide all the water that the air can hold. And the carbon dioxide plays this role in the biological cycle of animals and plants. By animals exhale or emit CO2, and plants absorb or breathe or use CO2. And this is important to the composition of the atmosphere as well as to the balance of energy. So the question that we are faced with here, we force the atmosphere with increased CO2. What is the response? Then the question comes down to, do we have a damping effect? Does the atmosphere respond by damping it, or does the atmosphere respond by amplifying it? There's a classic paper by Soden and Held which go through these in much more rigorous detail, looking at their effects in both the climate observations and in models. We can think of feedbacks to the physical climate system, and then we can think of feedbacks that are associated with chemical reactions in the atmosphere and feedbacks associated with biological responses. We're going to focus in this module specifically on those of the physical climate system. The first feedback is one which is sometimes called the Planck feedback or the temperature feedback. And it's the basic idea that in this balance that we have between the energy coming from the sun and the energy Earth is emitting to space, that if we're in a balance and heating is equal to cooling, we know that cooling is proportional to temperature, which we generally write as this sort of lambda T. So if the heating is not changing, if something happens to perturb and make the temperature more positive, that's a positive increase in temperature, what happens is that it just cools more in that case, and it comes back to equilibrium, and it comes back to equilibrium on a time scale that is some way proportional to this term lambda. So what we are actually doing in the carbon dioxide increase problem is changing this lambda. However, this feedback of the warming temperature still has a strong and moderating effect, because the amount of heat that is released by the Earth, that is, how fast does the Earth cool back to space, is proportional to temperature. In fact, it's proportional to the fourth power of temperature through something known as the Stefan-Boltzmann law. For the next feedback, it is important to think of that role of water. If you look at a plot, which I have here, of temperature in degrees Fahrenheit versus the ability of air to hold water, you'll see that as temperature increases, the ability of air to hold water also increases. This leads to the very strong positive feedback associated with water and water vapor. If you look at sort of typical climates around the world, you can see that we have hot and wet climates, we have hot and dry climates, we have cold and dry climates, and cold and wet climates, which I've indicated on this graph of temperature versus moisture. And the strong relationship between water and climate can perhaps become, again, more intuitive by thinking of different places in the country, in the United States. So Florida is hot and wet. Arizona would be a hot and dry climate. Colorado in the winter would be a cold and dry climate. And Michigan in the winter would be a cold and wet climate. What we see here is that in these dry climates, they're a long way away from the ocean, or their atmospheric circulation patterns are such that they do not get a lot of oceanic moisture. Florida and Michigan, on the other hand, have either, say in this case, the Atlantic Ocean and the Gulf of Mexico, or in this case, the Great Lakes. So there is a major supply of water. The basic idea of the water vapor response is the CO2 warming increases the temperature. That then increases the moisture in the atmosphere, assuming there is a source of moisture such as the ocean or the lakes. This then increases the greenhouse effect. Once the greenhouse effect of the water is added on, this increases the temperature again. And we get this situation here, like this, where it could actually run away. Higher temperature, again, causes evaporation from land and ocean. Higher temperature allows more water to be held within the air. And this water is a greenhouse gas, so it effectively increases the thickness of the atmospheric blanket. This could run away, meaning that it could continue to get warmer and warmer as a response to that initial burst of warming from the carbon dioxide. The next feedback I want to talk about is the one that's associated with ice and snow and the reflection and absorption of energy associated with ice and snow. Both ice and snow, in their clean state, are primarily reflectors. When I say clean, one of the issues of climate and climate change and pollution is soot and soil often dust from agriculture, falls on the ice and changes its color, essentially turning it from a reflector to more of an absorber, or at least a weaker reflector. But if we focus primarily here on ice, it's primarily a reflector. If the temperature increases, then ice melting increases, ice itself decreases, reflection decreases, and ice is usually replaced by a more absorbing surface. It's quite similar for snow, but snow is a little bit of a different beast. We have this interesting phenomenon that goes back to the ability of air to hold water based upon temperature, that when it does snow, so when it's cold enough to snow, there's likely to be more water in the air, and so you might get more snow, but the snow stays on the ground less, and it might snow less often because it's not cold enough to snow. In some places, snow turns into ice. That's how glaciers are formed. It's complicated, but in general, if there's less snow cover on the ground, as we see in a warming Earth perhaps, the ground is clear in a place like Michigan by April rather than by May, perhaps sometimes in the past. Again, we move from a situation where we have more of a reflector to an absorber. But I think the idea is really here to focus on the ice, the glaciers, the ice sheets, and sea ice, that we have something here known as the ice albedo, or the ice reflection feedback, where less ice means less reflection, warmer means less ice, and again we have a situation that could run away. Some people view that the start of the ice age and some of our cooling periods is perhaps the other way here. It gets a little colder, we get more ice, and then we have more reflection, and then that makes it a little colder still. And this leads to an interesting thought experiment anyway, that's often called the ice-covered or the snowball Earth. We then get to the most complicated of all of the feedbacks in this physical climate consideration, which is clouds. So when we looked at the balance of the energy in the Earth, we saw that clouds reflected radiation from their tops, but looked at from the surface of the Earth, they were very good absorbers and emitted infrared radiation back to the surface. So clouds are complicated. Warmer means more water, more clouds. More clouds means more reflection of solar, which is a cooling effect. More clouds mean more infrared to the surface, which is a warming effect. And then we have this whole role of the aerosols, these particles in the atmosphere, which change the optical characteristics and they change the precipitation rates of clouds. So clouds in and of themselves are this competing cooling and warming effects. So we actually have to calculate a budget rather specifically based on the attributes of the clouds. If we look at this, we could view this as a potentially stabilizing effect. I think that an essential point to take away is that water in all three phases is essential to a stable climate, and as I'll discuss in more detail in a minute, the amount of ice that is present on the planet at any time is a pretty good measure of our climate system. So the cloud-ice atmosphere feedback, warming and cooling is possible. There's a lot of discussion about cloud and aerosol effects. Anytime that there's a lot of discussion, you could say that it's a subject of high uncertainty. And how clouds change has been much argued, and there's an interesting paper by Arthur Howell and Dick Lindzen called The Iris Effect, which made arguments of almost a self-correcting atmosphere based upon this cloud-ice atmosphere feedback. It's an effect that we know is physically plausible, But when we do the budget, there is really no evidence of a completely compensating effect like the biological activity of the human iris, which was the simile or the metaphor that they were using here. So if we were to do a status check of the feedbacks in the physical climate system, the feedbacks we've discussed so far are the ones that are most intuitive. We have a positive feedback associated with water vapor and ice albedo. We have negative or positive feedbacks associated with clouds. And then we have this stabilizing effect, which is characterized as a negative feedback of infrared emission, or the Planck feedback, which is basically that the amount of energy that is released to space and hence cooling to the Earth is proportional to the temperature. There are a lot of other feedbacks in the physical climate system associated with ocean, land, and again ice, which will not be discussed in detail in this module. The ocean is accumulating heat and carbon dioxide, so can it be released? Can a little bit of temperature increase cause a CO2 increase and hence start a feedback loop? The answer is yes. Can the heat transport by the ocean be changed? Sea ice is frozen ocean. So if the sea ice is changing, if it is melting, then it changes the way there is reflection of solar radiation from the sea ice. But the sea ice also serves an important role of being an insulator between the air and the water. And so it changes the heat transport, or the heat exchange between the land and the ocean. And then even more complicated is this idea of salt in the ocean, salinity, which is associated with the density and transport. So as water melts off of glaciers and that water is fresh and it comes out onto the ocean, it can change the ocean's circulation. And again, over on land, one of the things we are most concerned about is the carbon dioxide and the methane stored in the frozen land or the permafrost. Can it be released? There are the issues of changing snow and ice cover on land. And then there's the direct effect on land of changing the absorption and reflection because of land use, such as forests, cities, and agriculture. So in conclusion, the feedbacks, we think about equilibrium balance with the sun. That is, the Earth's cooling to space is proportional to temperature. And so this Planck feedback, this temperature-related emission to space, is a strong anchor of our climate, and that remains true even as we increase carbon dioxide. The ice albedo and the water vapor feedback are positive, and they're very strong and definitive, and we can already measure them. Clouds can go either positive or negative. We have not talked about the complex roles of aerosols, but aerosols themselves can have heating effects, cooling effects, or they can influence clouds and change whether or not clouds have a positive or a negative effect. And taken in summary at this point, if we look at theoretical and observational investigation, we do conclude that what we are experiencing, the feedbacks, are substantially linear and positive. Therefore, we can say that the response of the Earth to carbon dioxide heating is to heat up even more. With that, thank you for your attention.